My dear students, myself Kiran MP, Assistant Professor in the Department of Computer Science and Engineering in Government Engineering College, Kushalnagar. I welcome all of you for this session on Cartesian product and relations. Now let's have a look at agenda of this session. At first, I am going to give you an introduction to what is known as Cartesian product, also referred as cross product. The prerequisites for Cartesian product or cross product is sets. Hope all of you are familiar with the basic concepts of sets. I mean to say, you might have heard and you might be familiar with what is known as set, subset, power set, null set, and so and so. Okay, so once we get familiar with Cartesian product, let me have a discussion about what is known as relations. Okay, now let we study in detail about Cartesian product. As I said, the prerequisite for proceeding with Cartesian product is a set. So you all know what is set. Set is nothing but some collection of elements, right? So now assume you are given two sets. Let it be labeled as A and B. Okay. Now what actually the Cartesian product or cross product of these two sets A and B is nothing but a set. Okay, I repeat, the cross product or Cartesian product of any two sets is nothing but a set. But in this set, the elements are an ordered pair. I mean to say, in this set, the all elements appear in the form of an ordered pair, say A comma B. Okay, where the element A belongs to set A and element B belongs to set B. Clear? So what actually Cartesian product or cross product of any two sets A and B is nothing but the set of all possible ordered pairs A comma B, where element A belongs to set A and element B belongs to set B. As you can see on the slide, this cross product or Cartesian product of A and B symbolically represented as you can see on the slide, A cross B equals an ordered pair A comma B, set of, it's nothing but the notation says that opening plow bracket says it's a set of ordered pairs A comma B, such that this the first element of an ordered pair, that is A, belongs to set A, and the second element of ordered pair A comma B belongs to set B. Okay, clear? So now in general we know in arithmetic, okay, let me say when I say product of any two numbers, say the product of 3 and 2, okay, product is commutative, right? I mean to say 3 into 2 equal to 6 is nothing but 2 into 3, right? But here I need to highlight the cross product or Cartesian product on any two sets, say A and B, need not be commutative. I mean, the cross product A cross B is not equal to B cross A in general. Why? I mean, because the cross product B cross A, as you can see on the slide, okay, is nothing but a set of all possible ordered pairs B comma A, where the first element of an ordered pair here it belongs to the set B, and the second element of an ordered pair belongs to set A. So this justifies the cross product or Cartesian product of any two sets need not be commutative. Okay. So now let me add a look at an example. Okay. As you can see on the slide, okay, and first example, I have taken two sets. The first set is labeled A and consists three elements 2, 3, 4. And the second set is labeled B and it contains two elements 4, 5. I repeat, the first set A contains three elements 2, 3, 4. And the second set B contains two elements 4, 5. Now, let me see first how we can compute A cross B. Okay. As you have seen in the first slide, in symbolic form of A cross B, what actually it is represented as? It's a set of ordered pairs A comma B, right? In this ordered pair A comma B, the first element A is an element of set A and the second element B is an element of set B. Got it? So now for this example, okay, A cross B, okay, in the means I need to list all possible ordered pairs of the form A comma B, where A is an element of set A and B is an element of set B. Okay, as you can see in example, for an element A of ordered pair, there are three possible values 2, 3, 4. And for each of these possible values assigned to element A, there are two possible values for an element B, that is 4 and 5. So A cross B consists an ordered pairs 2, 4, the next ordered pair 2, 5, the next ordered pair 3, 4, the next ordered pair 3, 5, the next ordered pair 4, 4, and the last ordered pair 4, 5. Okay. Now similarly, to compute B cross A, okay, as we can see in the first slide, B cross A is nothing but set of all possible ordered pairs of the form B comma A, where B is an element of set B and A is an element of set A. So for this example, okay, the first element of ordered pairs can be substituted with two values 4 and 5, and the second element of this ordered pair can be filled with three values 2, 3, 4. Okay, so we get B cross A to be the set of ordered pairs 4, 2, the next ordered pair 4, 3, the next ordered pair 4, 4, the next ordered pair 5, 2, the next ordered pair 5, 3, the next ordered pair 5, 4. So I hope all of you are familiar with computing the cross product A cross B and B cross A. And with this example, you all got justified that cross product is not commutative. I mean to say A cross B is not equal to B cross A. So one more thing, in arithmetic we used to compute square, we used to compute cube, right? I mean to say we used to compute 2 square, we used to compute 2 cube. Similarly, we can apply cross product on the same set. Okay, I mean to say, suppose assume that in this case, okay, the set B is nothing but set A. Then I mean to say, if I am computing A cross B, it means I am computing A cross A. Got it? What I assume, the set B to be same as set A. So in this case, when I compute A cross B, it implies I am computing A cross A. Okay. In this case, A cross A is nothing but set of all possible ordered pairs A comma B, where both A and B are elements of set A. And you can see in the symbolic form, right? A cross A equals set of all possible ordered pairs A comma B, such that A belongs to capital A and B belongs to capital A. Capital A represents set. Lowercase I need to highlight. The caps letter represents sets. Caps letters represent sets. Lowercase letters represents elements of that set. Okay. So the product A cross A can also be denoted as A square. Now, the cross product can also be represented pictorically. Okay, and this pictorial representation of cross product, I mean Cartesian product, is known as tree diagram. Okay, let me see how we can construct a tree diagram for the cross products A cross B as well as B cross A for the same previous example. Okay, thus for the same previous example, that is set A consists 3 elements 2, 3, 4, and set B consists 2 elements 4, 5, and as you can see, A cross B and B cross A consist 6 ordered pairs, right? But we know A cross B is not equal to B cross A. Now let me tell you how we can construct a tree diagram for the first cross product A cross B. Okay, and just look at the tree diagram in the first part labeled as A cross B. Now the tree diagram, the tree diagram for any cross product, say A cross B, proceeds from left to right. I repeat, tree diagram for cross products proceeds from left to right. From the leftmost end point, 3 branches originates. As you can see on the slide, for the cross product A cross B, from the leftmost end point, 3 branches originates, labeled as 2, 3, 4. Okay, as there are 3 elements in set A. And from each of these labels, 2 more branches originates. From each of these labels, 2 more branches originates. Okay, one for element 4 and the other for element 5 of set B. Okay, and these points are labeled as ordered base. Okay, so as you can see in the slide, the right in the first part of the first tree diagram, the right labels, okay, the rightmost labels are nothing but the ordered base, okay, is nothing but the elements of A cross B. Okay, now let me have a look at constructing tree diagram for B cross C. As I said, the tree diagram starts from left to right. Got it? So here there are, now I am constructing tree diagram for B cross A. Is it? So in B there are two elements 4 and 5. So from the leftmost end point, in this case two branches originates. One labeled as 4, the other labeled as 5. And from each of these labels, 3 branches will originate, one for each element of set A. Okay, and these points, okay, are labeled as an ordered base. As you can see on the slide, 4, 2, 4, 3, 4, 4, 5, 2, 5, 3, 5, 4. These are nothing but the ordered base elements of B cross A. So you are familiar with how to compute cross product or Cartesian product of any two sets. Also, I hope you are familiar with constructing a tree diagram for the cross product or Cartesian product of any two sets. Now, let me analyze the size of any Cartesian product. Okay, I mean to say, let me analyze the size in general, what we call as cardinality of the cross product of any two sets. Okay, let me assume the sets A and B to be finite. Okay, and set A contains m elements, that is, as you can see on the slide, size of A equals m, and let set B contains n elements, n, as you can see on the slide, size of B equals n. Okay, then the size of A cross B is nothing but the product mn. Okay, so let me justify looking at a previous slide. See here, in this example, the size of A is 3, right? Because there are 3 elements. And the size of set B is 2, because there are 2 elements. And you can see in this, in A cross B, there are 6 ordered base, means 6 elements. Similarly, in B cross A, there are 6 ordered pairs, 6 elements. Okay, so size of A in this case it is 3, size of B in this case it is 2. So size of A cross B is 3 into 2 equals 6. Size of B cross A is 2 into 3 equals 6. Got it? So, in example 2, there is an assumption that set A has 5 elements, okay, and set B has 8 elements. Assumption set A has 5 elements, set B has 8 elements. Then A cross B will contain 5 into 8, that is 40 elements. Similarly, B cross A will contain 8 into 5, again 40 elements. What about A square? A cross A, it contains 5 into 5 equals 25 elements. And B cross B, it contains 8 into 8 equals 64 elements. So, now let me have a look at one important topic of set theory, that is subset. I think all of you have heard or might be familiar with subset. If not, let me tell you. See, assume you have given two sets, okay, say first set and second set. There are two sets, let first set and second set. If all the elements of first set, I repeat, if all the elements of first set exist in the second set, then we call the first set to be subset of second set. Clear? If all elements of first set exist, I mean present in the second set too, then we call first set to be subset of second set. As you can see in the second point of subset, okay, the symbol that is used to denote subset. Now, one more thing you need to know. If A is any set, okay, and its size is M. I repeat, if A is any set and its size is M, then the number of subsets that are possible is 2 power M. I repeat, if A is any set with M elements, then the number of subsets of set A that are possible is 2 power M. Okay, of this 2 power M subsets, there are two special subsets. Of this 2 power M subsets, there are two special subsets. One is a null set which doesn't contain any elements, and the other one is a set A itself. Okay, so I repeat, of the 2 power M subsets, there are two special subsets. One is a null set and the other one is set itself. Now look at example 3. Set A contains 5 elements. 1, 2, 3, 4, 5. And set B contains 2 elements. 2, 3. As you can see in example 3, all elements of set B, that is 2 and 3, also exist, I mean also present in set A. So now we can call B as subset of A. But we can't call A to be subset of B. Why? Because set A consists elements 1, 4, 5 which are not in set B. Okay, so we can't call A to be subset of B, but we can call B to be subset of A. And it is denoted as B subset of A, as you can see in the last line of slide. Now we will proceed with the second agenda of this session, relations. So what actually relation means? See, you are given two sets, A and B, and this two set contains some elements. Okay, relation here, it means some elements of first set might be related to some elements of second set. I mean, the elements of set A might be related to some elements of set B. Okay, clear? So those elements of set A which are related to elements of set B, I can represent them as an ordered pair. Okay, clear? If there exist some elements of set A related to some elements of set B, I can represent them as an ordered pair A comma B. Okay, and all those ordered pairs, I'll consider it to be a set. Okay, and this set is nothing but a subset of A cross B. Okay, I repeat, we have two sets A and B. Some elements of set A might be related to some elements of set B. And those related elements, okay, I will represent as an ordered pair. And I will form a set of this ordered pairs. And we can analyze, okay, that this set which consists ordered pairs, which represents those elements of set A and set B which are related. Okay, and this set is a subset of A cross B. Okay, and this subset of A cross B we call a relation from A to B. Got it? So what is relation from A to B? Is nothing but any subset of A cross B. Okay. Now suppose if you have computed B cross A. Okay, when you have computed B cross A and we have a subset of B cross A, we have the subset of B cross A, then in that case we call it's a relation from B to A. Got it? So there is difference between, I mean to say, relation from A to B is different from relation from B to A. So what is relation from A to B? It's a subset of A cross B. What is relation from B to A? It's a subset of B cross A. Now let me analyze how many relations may exist from set A to set B. Also, how many relations might exist from set B to set A? Now, let me assume set A to contain m elements. That is, size of A equals m. And let me assume set B to contain n elements. That is, size of B equals n. So, how many elements exist in A cross B? We know A cross B contains mn elements. Is it? So, I repeat, A contains m elements, B contains n elements. Then A cross B contains mn elements. Okay. Now, coming back to previous slide, look at the third point of subset. What states, if any set A contains m elements, if any set A contains m elements, then there are 2 power m subsets of that particular set A. Got it? 2 power m subsets of set A. Okay. Now, here we are interested in determining number of relations from A to B. Is it? Number of relations from A to B. And we know relation from A to B is nothing but subset of A cross B. Subset of A cross B. So now, to determine number of relations from A to B, I need to determine number of subsets from A, number of subsets of A cross B. Got it? I repeat, relation from A to B is nothing but subset of A cross B. So, relation from A to B is nothing but subset of A cross B. So, first I need to determine number of subsets of A cross B. And thus, that number of subsets of A cross B is nothing but number of relations from A to B. So now, first I need to determine how many subsets we can have for a set A cross B. See, if A contains m elements and B contains n elements, then A cross B contains mn elements. I repeat, if A contains m elements and B contains n elements, then A cross B contains mn elements. Is it? So A cross B contains mn elements. So we have 2 power mn subsets of A cross B. So we have 2 power mn subsets of A cross B. And all these 2 power mn subsets of A cross B are nothing but relation from A to B. Now similarly, to determine number of relations from B to A, B contains n elements, A contains m elements, then B cross A contains n m elements. So B cross A contains nm elements, so we have 2 power nm subsets of B cross A. All these subsets of B cross A or nothing but relations from B to A. Now we have seen relation from A to B as well as relation from B to A. Okay, now we will add a special relation, okay, what is known as binary relation, which is known as binary relation. See, in some cases, the element of a set might be related to some elements of its own set. I repeat, an element of a set might be related to some elements of its own set. Okay, in that case, the relation we call a binary relation. Okay, I repeat, in some cases, an element of a set might be related to elements of its own set. In such case, a relation we call as binary relation. As you can see in the third slide, as you can see in the third point on the slide, if R is the relation from A to A, if R is the relation from A to A, that is, R is a relation from A to A means R is a subset of A cross A. Okay, then we call R is a binary relation on A. Now let me have a look at example 4. See here, we have given we have taken the same sets A with 3 elements 2, 3, 4, and B with 2 elements 4, 5, and we have A cross B as well as B cross A, and we have seen how to compute A cross B and B cross A in earlier. Right. So we can see A cross B, B cross A to contain 6 ordered pairs. Okay. Now let me see some relations from A to B and some relations from B to A. So what actual relation from A to B is nothing but subset of A cross B. What actual relation from B to A is nothing but subset of B cross A. So let me look at some relation from A to B and some relation from B to A, and few which are neither relation from A to B nor relation from B to A. Now look at first set with 3 ordered pairs. Look on the slide. Okay, the first set with 3 ordered pairs 2, 4, 4, 5, 4, 4. So this first set with 3 ordered pairs 2, 4, 4, 5, 4, 4 is nothing but subset of A cross B. Is it? Just check it. Just verify on the slide. The first set with 3 ordered pairs 2, 4, 4, 5, 4, 4 is a subset of A cross B. So we can call this as relation from A to B. Similarly, look at the second set with 2 ordered pairs 4, 2, 5, 3. This second set is nothing but subset of B cross A. So we can call the second set to be relation from B to A. Is it? So clear, right? The second set is a subset of B cross A, and hence we can call its relation from B to A. Now look at the third set. It contains two ordered pairs, 2, 3, 5, 3. I repeat, look at the third set consisting two ordered pairs, 2, 3, 5, 3. These two ordered pairs neither belong to set A cross B, nor they belong to set B cross A. Is it? I repeat, the two ordered pairs 2, 3, 5, 3 of third set neither belong to A cross B, nor they belong to B cross A. So they are not subset of A cross B or B cross A. So they are not relation from A to B as well as not relation from B to A. Now, in this example, let me see. Suppose you are given two sets with few elements and you are asked to determine how many relations from one set to other set. Okay, so let me see how to solve that and those such problems. So we have given set A with three elements 1, 2, 3. And set B with three elements 2, 4, 5. So, and you are asked to determine number of relations from A to B, number of relations from B to A. So to determine number of relations from A to B, you need to know number of subsets of A cross B. Similarly, to determine number of relations from B to A, you need to know number of subsets of B cross A. So, to determine number of subsets of A cross B, I need to know number of elements of A cross B. Similarly, to determine number of subsets of B cross A, I need to know the number of elements of B cross A. So let me compute first number of elements of A cross B and number of elements of B cross A. So size of set A is 3, size of set B is again 3. So size of A cross B is Mn, which is 9. A cross B is Mn, which is 9. That's 3 into 3. So A cross B contains 9 elements, 9 ordered pairs. So number of subsets of A cross B is 2 power 9. So number of subsets of A cross B is 2 power 9. And hence 2 power 9 relations from A to B. Is it? Hence 2 power 9 relations from A to B. Suppose if I want to compute how many binary relations on A. How many binary relations on A? Okay, I need to determine number of subsets of A cross A. A contains 3 elements, so A cross A contains 3 into 3, that is 9 elements. So there are 2 power 9 subsets of A cross A, and all these 2 power 9 subsets of A cross A we call binary relations on A. Clear? So In this session, we have discussed about Cartesian product. Okay. Also, we have discussed about relations. Okay. This was agenda of this session. Okay. Let me wind up this session. Thank you for listening.